I'd like to work out a few more of the free response questions that you have for practice on the kinetics unit. I'm hoping to get number 5, number 8, and number 10 into this video. Number 5 starts out with two reactions, and their equations are given there at the top. They're also giving us a potential energy or coordinate diagram where reaction 1 has already been drawn in. So we can see that reaction 1, which is A plus B, makes 2AB here in the beginning of the problem, is drawn as the curve there, and it's shown to be exothermic. You can tell because it starts out high and ends up low. And then they've started to draw in the graph for the other reaction, for reaction number 2, which starts out with X and Y and forms two XY molecules. And so you can kind of see they've started to draw that in here. That's intended to be this second kind of line right here, slightly higher on the left side than the first line that was drawn in completely. And they're going to ask us right away to finish the drawing for reaction 2, draw in the reaction curve or potential energy diagram curve for reaction 2. And there's some key information in the paragraph that starts out. The potential energy diagram for reaction 1 is shown. The potential energy of the reactants of reaction 2 also indicated, as I mentioned there. Reaction 2 is endothermic, and the activation energy of reaction 1 is greater than that of reaction 2. So there's going to be some overlap here with two curves in the same graph. This isn't terribly common, but it is a way to kind of compare them fairly. That way you don't have to worry about the scale of your y-axis. If they gave us curves for two different graphs, rather two different curves on two different graphs for the two reactions, they'd also need to give us a sense of the scale on the y-axis. Otherwise, you wouldn't know if the units were scaled the same, and if you could even compare the two graphs, like, fairly apples to apples, or if they would be completely sort of skewed by just how the things were scaled. So by putting them on the same graph, they do allow us to compare them a little bit more fairly and a little more confidently. But because reaction 2 is endothermic, we need to show it gaining overall in energy, or ending up higher in energy than it starts. So I'm going to use, I think I'll use my green here just to kind of make it stand out a little bit. We're going to start over here as a reactant at the beginning, and then we're going to need to end with products that have a greater energy. So I'm going to have them end up here someplace. It's kind of slopey. Let's try that again. And then it also mentions that reaction 2 and reaction 1 have different activation energies. In fact, the activation of reaction 1 is greater than that of 2. So the activation energy for my reaction can't go up as high as that first one. Maybe something just like that. And so the activation energy of that second curve is less than it was of for the first one, and yet it's still showing it as an endothermic reaction. So we end up here. It's not lining up very well when I draw. But if I were to label that, then this would be 2xy, just to kind of finish the way that they labeled that first one. Okay, for reaction 1, predict how each of the following is affected as temperatures increase. The rate of reaction, we've talked about this before. Rate of reaction will increase for any reaction as temperature is increased. And while I won't write out a ton of answers here in terms of description, I will talk through them. And if you're listening along, then I would say put them into your own words, paraphrase however you feel you need to. We've talked a bit about this before, that when you raise the temperature of matter, you're increasing the kinetic energy or the velocity of the particles, especially if we know that they're gases. In this case, we don't know that they're gases, but it's easiest to sort of imagine that gas particles move faster when they're heated. Liquids and solids do the same. They're vibrational energies, or they're just their movement around in a fluid like liquid. The particles are going to move more quickly. And because particles that are warmed move more quickly, they collide with each other more often, and they collide with each other more forcefully. So there will be more effective collisions between particles of A and B, or diatomic A and diatomic B in that first reaction. There would be more collisions and more effective collisions, so there'll be more collisions that have sufficient energy to achieve the activation energy, and the rate will increase. But what about the enthalpy of reaction, or delta H, as we usually label it here? What will happen to that? And delta H will be unaffected if we change the temperature. Delta H is sort of described by, or determined by, limited by, the energy required to break bonds and the energy released as bonds are forming. And those values, those bond energies, those things don't change when temperature changes. Perhaps the reaction might become more or less thermodynamically favorable, as we change temperature. But in the case of delta H itself, that value does not change when temperature is changed. The only thing that can affect delta H is if you were to change the actual energy of the reactants or products themselves, and that's really not possible to do, right? We could find maybe a pathway that has one or two or three, two or three additional steps, and if there are steps to the mechanism, then perhaps each step could have a delta H value that is affected by, say, using a catalyst or something. But the overall delta H will be unaffected for the reaction equation, pretty much regardless of what you do. Okay. For reaction 2, the form of the rate law is rate, and they're giving us here x to the m and y to the n. This is the typical form of any reaction rate law. Describe an experiment that can be conducted in order to determine the values of m and n in the rate law for the reaction. When that's the way that the question is being phrased, the way that I would think about designing an experiment, I would say we want to typically perform an experiment where we do what we see with differential rate laws, with several trials. In some trials, hold x constant, for example, while y is doubled. And monitor the rate. And in other trials, we'll just kind of do the opposite. We'd say y is held constant, while x is, say, doubled or tripled. And that's where we get to our differential rate law. And we come up with ways of kind of examining data from various trials to see what happens when I double x, what happens to the rate. If the rate is doubled, then it's first order. If the rate is quadrupled, then it's second order, for example. Doubling a concentration will double rate. If first order, it will quadruple rate. If second order, and not affect rate if zero order, etc., etc. That kind of idea. And that's how we'd come up with those m and n rate orders for each of the reactants. So describing it in terms of differential rate law calculations. So it's really sort of a long way of saying use the differential rate law with several experiments. Now I'm not sure that would be enough. So I wouldn't necessarily say that we want to just write that. But I think this is kind of a very verbose sort of an answer. I don't know if any more in 2020, if the question would be asked where you'd have to describe that, but that's the basic idea. Having you recognize that the best way to come up with those simple fashion is to look at a series of trials where we can hold some things constant and vary the others. Having those control variables and then having independent variables that can tell us how the rate is going to be affected as a result. From the information given, determine which reaction initially proceeds at the faster rate under the same conditions of concentration and temperature. So what they're sort of saying there is, what if A and B and X and Y were all the same concentration? Let's just say they're all 1 mole per liter, just for simple numbers. And then the reactions are going to happen at the same temperature conditions as well. So let's say at 300 Kelvin, for example. Which reaction will proceed faster if everything's sort of being held constant? And hopefully you'd recognize that reaction rate, under that sort of description, reaction rate will be a function of activation energy. And so since reaction 1 here has the higher activation energy that was described right out of the gate in our opening paragraph, if the activation energy of reaction 1 is greater than that of 2, then under those similar conditions, the rate of reaction 1 will be slower than that of reaction 2. So reaction 1 will have a slower rate because its activation energy is greater. And you can write out activation energy, or you can abbreviate it. And then don't forget, when you use comparative words like greater, don't just end on greater. Greater than what? Greater than reaction 2's activation energy. So saying that they're at the same temperature means the particles would all have the same velocity, and so their collisions, we would sort of suggest, would have the same energy. Then it's just a matter of what barrier are they trying to achieve or overcome, and that barrier is the activation energy. So if their collisions are all equal, then the difference will be which one has an easier time of it. In other words, which reaction has the lesser activation energy. And they gave us that answer kind of right at the beginning of the problem. All right, let's take a look here at 8. The first order decomposition. So right away we know it's first order, and that's an important thing to catch. They often put that in the phrasing of the opening of the problem. The first order decomposition of a colored chemical species X into colorless products is monitored with a spectrophotometer by measuring changes in absorbance over time. So a spectrophotometer, just a device that measures the intensity of color in a solution by shining light through it and measuring how much of that light is being absorbed and how much is being transmitted. So they're measuring how the absorbance is changing over time. Absorbance is a measurement of how much or what sort of portion of the light source is being absorbed by the solution, and that has to do with complementary colors and those kinds of things. So with X decomposing into colorless products, let's just go with X becoming Y and Z. And we don't really need to know much about Y and Z other than if they're colorless, and that it's first order. So we have, for our right then, rate equals K times X because it's first order. And that's all based on just the opening paragraph. Species X has a molar absorptivity constant of 5 times 10 to the third centimeters to the -1, and then molarity to the -1. Path length of the cuvette contained in the mixture is 1 centimeter. So this is just describing sort of the standard description of a spectrophotometer setup, and that is to describe the size of the cuvette and the absorptivity constant, which is all part of the calculation using the equation on your formula sheet of A equals A times B times C. Usually the format it's given in. Here, they're asking us to calculate the initial concentration of the colored species. And so the quickest way to do that is to use that formula from your formula sheet. And so if you haven't got that formula sheet in front of you or nearby, pull that out and find that formula that's on there. We don't use it a ton. It kind of happens when we look at mixtures. It happens when we look a little bit at solutions. We use it a little bit in even first-year chemistry when it comes to absorbance. But the equation on our formula sheet, A equals ABC, and some, I guess in the 2019 version, the most current version, I'm seeing that instead of A, which is kind of the standard way I've always seen it used most often, you'll see this sort of little epsilon symbol. I think that's epsilon. And that little epsilon stands for that molar absorptivity. So on our formula sheet, A is the absorbance. That little Greek symbol there is the molar absorptivity constant, which they gave us. B is the path length, and then C is the concentration or molarity of the solution. So if they want us to find the concentration, then we're just going to use that equation and solve for C. So go down here below. C will be A over epsilon B. The absorptivity, the initial concentration, that'll be at time 0 in my data table, so they're asking me to fill this in. The absorbance is 0.600. So 0.600, and absorbance doesn't have any units, so that works out relatively simply. Absorbance is based on a log calculation, and so when we do log or natural log, the units just sort of go away. The absorptivity constant, 5 times 10 to the third, and then the path length is 1 centimeter. So 5 times 10 to the third centimeters to the -1, molarity to the -1. Standard units kind of on molar absorptivity there. And then the path length is 1 centimeter. Okay, so if we calculate that, we're going to multiply that, punch it in here. Do our quick calculation. I don't have my calculator in front of me, so pardon me. 0.6 divided by 5 times 10 to the third. and that's positive third, which is kind of unusual. We haven't used a lot of positives here. Concentration, or rather, concentration is 1.2 times 10 to the negative 4 molarity. The initial concentration, 1.2 times 10 to the negative 4 moles per liter. So I can't quite write small enough to fit that in the box here, but it is good to consider, does it make sense? And the concentration has been dropping with time in this data table, and the absorbance is dropping with time as that is being converted to a colorless species. The absorbance would drop. And so the answer that we came up with there, 1.2 times 10 to the negative 4, makes sense in light of the other values that are in the table. It should start out at highest concentration, and then gradually it's used up with time. So that does make sense in light of the other information that was given to us. All right, let's take a look at letter B on this problem and see if we can calculate the rate constant for the first order reaction using the values given for concentration and time. First of all, we know it's a first order reaction. They said it again there. It was also in the opening prompt. And the reason that that's so valuable is because if we go to our formula sheet here, recognize that we've got three important equations, actually all four, but these first three sort of make a set. This is for a zero order, this is for a first order, and this is for a second order reaction. So zero order, first order, second order. And since this is first order, we're going to want to use this equation right here to answer the question that's in front of us. In fact, we'll use it for a couple of questions that are left. We can find any of the values within this equation using the others. And in this case, they want us to figure out the rate constant. So they want us to figure out K. And so I'm going to take that equation and I'm just going to rearrange it and get K by itself. And we've done this on previous problems, I think, if you followed along. But if not, this is important to go ahead and just do that rearrangement, I think, right away. So if we're looking at part C, this is C, right? Part B, pardon me. So if we're looking at part B and we're going to rearrange that equation to get K by itself, we'll have natural log of A at time t, and in this problem they've called ax, right? Instead of a, they're just using x. So I'm just going to go ahead and substitute that in. So the natural log of x at time t minus the natural log of x at time 0, or the initial concentration of x at time 0 there, equals negative kt. So I'm going to get the k by itself. I want the k to be by itself over here, which means I'll have divided negative t to the other side. So there's k sort of isolated on its own. And I should be able to plug in all the information that's left there on that question, or in that equation from that question. And I want to do that for initial time, for x, concentration of x at time 0, and then at some other time in the data table. So I'm just going to use the first two rows of my data table. We know the concentration at time 0. We figured it out in the last part of our problem. So that's 1.2 times 10 to the negative 4 molar. And then I also know the concentration at any of these other times. Well, a couple other times, 35 minutes in and 44.2 minutes in. So I'm just going to use that first line that we figured out earlier, because we want to use the initial concentration. And then I'm also going to use the concentration at time 35, or at 35 minutes. So that's 4 times 10 to the negative 5. And I'm going to just go ahead and substitute those values in. So the natural log of the concentration at time t, which I just said was 4.0 times 10 to the negative 5. So at time 35 minutes, 4.0 times 10 to the negative 5. And that's molar. Molar is going to go away when we apply natural log to it. The units kind of are gone. So at that point, we don't need to have the units anymore. But the natural log of that minus the natural log of our initial concentration, which we just found in the earlier part of this problem, 1.2 times 10 to the negative 4 molar. So that's my numerator. And then on the bottom I have negative t, and t is our time, which was 35 minutes. I chose the data at 0 and at 35 minutes. So this is how much time has elapsed, basically, since the initial measurement. And that's going to be set equal to k. So I go to my calculator and I plug all that in. Okay, natural log of each of those values subtracted, and then divide that by negative 35. And the answer should come up with here is k comes out at 0.0314. And the units, molarity, again, when I use natural log, molarity goes away. The units are sort of destroyed, I guess. And then we have minutes down here in the denominator, so minutes to the negative 1. And that's the typical units we would expect for a first order reaction, is time to the negative 1 as our units on the k value. So there we've got B. All right. For C, they want us to figure out how much, let's jump over here and take a look at C, how much time it'll take, or the number of minutes it takes, for the absorbance to drop from 0.600 to 0.0075. And it's, so in a sense, they're asking us in our data table here to fill in that question mark value that's missing. And again, we're going to think about this as, this is the concentration of x right, at, or sorry, the absorbance of x at time 0, and this is the absorbance of x at some later time, at time equals question mark, and that's what we're trying to figure out. Well, we know the absorbances, they're right there in the data table, first row and last row, which means we want to use the accompanying concentrations that go with them. So that's the one that we figured out earlier here, 1.2 times 10 to the negative 4. And then the last one in our table is 1.5 times 10 to the negative 5. So those are our two sort of relevant concentrations if we go back to and use that same equation. So I'm going to show you there's actually two different ways to sort of solve this out. So one way is to use the equation that we just used, and then the other way is to use half-life approach. And you can use either one, whichever one would occur to you first. And the idea, the hope, is that we'd get the same answer for both of them. Honestly, I've only worked out one of them, so I'm really hoping that they both give us the same answer. Otherwise, it's going to kind of disprove my whole point. So let's solve C using the same equation that we just used. Okay. In this case, they want to know how many minutes it'll take to get from one concentration to the next. So if we're using that first order equation from my formula sheet, I'm going to be solving for t. So I want to rearrange the equation to get t by itself, just like we did in the last one. So natural log of x at time t, which is what we're looking to find, minus the natural log of x at time 0, which we know, we found it earlier, equals usually negative kt in the equation. I want to get t by itself, so to have t by itself, I need to divide by negative k. So there's the equation that from the formula sheet rearranged to get time by itself. Let's go ahead and fill in the values that we know. At time t, the concentration was shown to be 0.0075, or I'm sorry, 0.075 in our data table. So sorry, that's the absorbance. I misspoke again. The concentration was 1.5 times 10 to the negative 5. There's our concentration. So this value at time t, 1.5 times 10 to the negative 5 molar, minus, and so that's, we need natural log of that, minus the natural log of the concentration at the beginning, which again we found earlier in the problem, right? 1.20 times 10 to the negative 4 molar, and then divided by negative k. Well, we just a moment ago figured out our k, 0.0314. We want negative k, so 0.0314. My pen's being a little cranky, I apologize. 0.0314 minutes to the negative 1. All right, and that's equal to t. So, as I said, this is not the method that I originally did when I worked this out myself, so I'm just going to take a moment here and punch this in. You can do the same if you like, and make sure that I get an answer that works out. Punching that numerator into my calculator, and then divide that by the negative 0.0314, and I get t equals 66.2 minutes. So it would take 66.2 minutes to get to that concentration. And if I go back to my data table and see if that sounds realistic, right? Looking at the data here, does that look reasonable based on the other concentrations and the other time? Yes, it would take longer to get to that lower concentration, according to this table. As the concentration drops, it takes more and more time. And so a value there of about 66 minutes would sort of make sense. The other way to kind of get to that answer is via the half-life approach. And that you kind of have to catch sort of as an eyeball test, I guess, in that sense. Notice what's happening with absorbance in this data table. Notice what's happening with absorbance. To go from 0.6 to 0.075, or even to go from 0.6 to 0.15, if you're kind of good at mental math, you might notice that those are all sort of multiples of each other. And so think about it as a half-life approach. In part C, they're really asking us to go from a concentration initially that has an absorbance at 0.600. So this is absorbance data. If the absorbance is cut in half, the molarity is also cut in half. So that would be the original absorbance cut in half, and therefore the molarity is cut in half. If we cut it in half again, we get 0.150. So that would be another halving of the original. And so that would be the molarity has been cut in half and then cut in half a second time. and then it's going another time smaller as well, so that's 0.075, and that's the initial absorbance that they refer to. And then this is the ending absorbance that they want to know how long it would take to accomplish that. And if you recognize that they're multiples of each other in that way, you could do this maybe a little bit quicker to see that this is cutting in half, this is cutting in half, and this is cutting in half. So we're down to 1/8 of the original concentration. We would recognize then that that represents 3 half-lives because we've cut it in half 3 times, 3 half-lives. And so the time required to get from 0.6 to 0.075 would be 3 half-lives. Now, do I know what the half-life is? I don't know it yet, but I can get it very quickly. And that's the other equation on my formula sheet. Half-life for a first-order reaction is 0.693 over K. That's right off my formula sheet. So that's 0.693 over the K value that we found earlier, 0.0314 minutes to the -1. If I punch that in my calculator, my half-life will come out to be 22, just a little under 22.1 minutes. That's my half-life. Well, if it takes 3 half-lives to get from the original absorbance down to 0.075, we would simply take this times 3, and we would get 66.3 minutes, or 3 half-lives, that would be necessary to get that change to occur. And what do you know? 66.3 minutes is the same thing that we found here just a minute ago. I mean, within 1/10 of a minute it is, and that's just some rounding differences. So whether you find t via the equation for the first order differential, or for the integrated rate law from your equation sheet, or if you recognize that this is actually representing 3 half-lives and do it via the half-life method, you should get the same answer for C either way. And just as a note, question D is going to ask you to find the half-life. So whether you did it by half-life approach or not, initially, you're eventually going to have to come back around to figure out that half-life for question D. And so that's again where you take the half-life for any first-order reaction, 0.693 over your K value, which we already found. And so our half-life was 22.1 minutes, as I showed there earlier in the alternate solution path for that question. And then for this assignment, as I'm giving it to you, questions E and F are removed. It's no longer something that you're going to have to be able to do, and so I'm not going to include it in this video. Hopefully that's good for question 8. If you have questions further than that on question 8, just keep a note of where they were, or if you didn't understand something that I did, and connect with me in office hours whenever we have a chance. Shoot me an email or something, and I'll try to help you out from there. We're going to move on next to question number 10. Okay, so on to question number 10. We have the decomposition of X to produce Y and Z, all gases, and in the equation given there. Data collected down below for a reaction in a 5-liter flask at 428 Kelvin. And the data is given in the data table and then the graphs that follow. So this is pretty typical in a kinetics question to be given data, to be given graphs, or maybe both. In this case, we have 3 graphs. Hopefully remembering that we're going to use those 3 graphs to determine what the reaction order is based on which graph is the linear one. In this case, clearly the one there in the top right with natural log of X is the one that's linear. And so just to kind of remember the values there, when concentration is linear here, the first graph, then we'd be looking at a 0-order reaction if this was linear, and it's not, so it's not a 0-order reaction. Natural log of X is the value on the y-axis for a linear graph if it's first order. We can see that it is in fact first order because this is our linear best fit line. And then the reciprocal of X, or the reciprocal of molarity of X, here as our second order setup. If that one was linear, then we'd be looking at a second order relationship, and it's not. So we've got a first order reaction here based on what we can just kind of catch in a glimpse in the graphs that are given. However, just because we know it's first order based on the graph, and we're going to probably need that later, doesn't mean the other graphs aren't of use to us, or that the other data in the tables isn't of use to us as well. So keep in mind they gave us 3 graphs. There could be information that we might find useful in those other graphs, and certainly in the data table where the data is far more precise than just looking at it off of a graph. It's much easier to take it out of the data table and have numbers that are more precise, more certain. Okay, so let's take a look at the questions. How many moles of X were initially in the flask? Well, moles of X, how much X is present? The data tables don't tell us moles of X, but they tell us initially, at time 0, the molarity of X was 0.00633 moles per liter. So our calculation for A is pretty simple based off of that, 0.00633 moles per liter, and it's a 5-liter container. So molarity times volume equals moles. And there's an equation on your formula sheet that tells you that molarity is moles over liters or moles over volume. And so that's our case here. Molarity times volume in liters is going to give us moles. We have a molarity initially of 0.00633 moles per liter, and that came right on my data table, times a volume of 5 liters. So there are 0.0317 moles of X present initially. Just right out of the data table and a quick mole conversion, we've got that figured out. That's the present number of moles present of X at the beginning. Question B asks how many molecules of Y were produced in the first 20 minutes of the reaction. We know typically when we're asked to find for molecules or atoms or ions or some number of particles, that's where we're going to use that Avogadro's number, 6.02 or 6.022 times 10 to the 23rd. Particles or molecules or atoms or whatever per mole. And so in this case, molecules per mole of anything, and specifically we're looking at Y. And it says in the first 20 minutes of the reaction. Now you might look at the data tables and say, well, there's nothing in here about Y, right? Everything here is about the concentration of X. And I can get that to moles, sure. I already did that in the first part of this question. But how do I get that and relate that to Y? Well, that's where our equation comes in. We're going to want to be able to look at the reaction equation and recognize that we have a 1:2 ratio, mole ratio of X to Y. And then Z has a 1 as well. But this is a 1:2 mole ratio for X to Y. That's going to be important to get to Y and relate it to the X, because we have all of this data for X, and we have a ratio that links any of that data directly over to Y as well. So in the first 20 minutes, what happened to X in the first 20 minutes? Well, its concentration, we can see here, decreased from 0.00633 down to 0.00427 moles per liter, right? So the concentration of X decreased as the reaction took place, and that's typical. X is a reactant, so its concentration will go down as some of those X particles are consumed by the reaction, and the amount of them that is still left will decrease. So if I want to figure out then how the Y relationship kind of links to that, we need to get to moles again. We need to be working in moles of X so that we can relate that to moles of Y. So the concentration change of X is going to be reflected in the concentration increase of Y, because as X is used up, Y is going to increase by a proportional amount, a 2-to-1 amount, right? So if we look at our change in X, we can use that to figure out eventually our change in Y as well. So how much did X go down? It went from 0.00633 down to 0.00427. And so for part B, we could say that concentration of X decreased in those 20 minutes. Just kind of want to write this out to think it out, but concentration of X decreased in 20 minutes from 0.00633 molar down to 0.00427 molar. And so that's a loss of 0.00206 moles per liter. That's how much of our X was lost, moles per liter. And again, take that times 5 liters, because we want to know how many moles were lost in a 5-liter container. That means that in the first 20 minutes, we lost 0.0103 moles of X. That's how much X was taken away in that first 20 minutes. And I'll show that there as a negative or a loss. But on the flip side, then, we're going to create 2 moles of Y. We're going to have a gain of 2 moles of Y for every 1 mole of X that's lost. And you don't have to show the negative signs here. You can just use them as sort of absolute values. So you could just treat it as positive 0.0103 moles and then use it as a simple 2-to-1 ratio. But I've kind of got the signs in here to kind of reflect our idea that we often find in our Rice tables, where the gain of Y will be related to the loss of X. So this would be like a minus X and a plus 2X if we were setting it up as a Rice table. And then the last step is to remember that we want to get this to molecules. So for 1 mole of Y, we have 6.02 times 10 to the 23rd molecules of Y being produced. And if I multiply that all out, that comes out to be 1.24 times 10 to the 22 molecules of Y that were produced in the first 20 minutes. So we went to the data table, we examined how X decreased in 20 minutes. We figured out what that equivalent quantity was in moles in that period of time using the volume of the container, and then we used a little mole ratio and a conversion step there to get that to the molecules of Y. So for C, what's the order of the reaction with respect to x? We already sort of said that this is first order with respect to x. And it's because the natural log of x versus time gives us our best linear fit. Okay. Gives a linear line of best fit, or best fit line, when graphed. All right. D, it wants us to set up the rate law expression then, and so rate would equal k times x to the first. And as usual with a decomposition reaction, the only reactant is x, so the only thing in my rate law should be x. And know it's first order, not because there's a 1 here, that's a coincidence, not because there's a 1 there, but because the graph of natural log of x versus time is the linear graph. That's how we know it's first order. So order does not necessarily come directly from the coefficients in the balanced equation. In fact, it's often the case that those would not agree. So don't automatically go to that assumption when you get to that point. Okay. And then they want us to figure out from that the k values. So the rate law expression, they want us to figure out k for E. Okay. So for part E, I need to figure out what the value of k is. Now, I don't have rate data necessarily for this reaction. I don't have rate data like we would have with, say, differential rate law problems, where we could go to the data table and just find the concentration of x and the rate that goes with it, and plug them in and find out what the k value is going to be. I don't have that sort of data here. So my alternative here, the other way to find k, one of several ways to find k, we could actually take the data from our data table here, and for natural log of x versus time, and we could actually have a graphing calculator, if you had one. We could have it do a linear regression of natural log of x versus time. So we could punch these data points into a calculator or a spreadsheet, even on Google Sheets or something, and we could have it do a linear regression and have it tell us what the slope of that line is. What's the slope of this line? Based on the kind of data that they're giving us here in the data points, we could probably do it from 2 points within this set of data as well. Just do change in y over change in x to come up with the value of k, being the absolute value of the slope of that line, or of any linear fit line. The k value will be the absolute value of the slope for whichever one's linear. Honestly, I like the go-to that uses the equations from our formula sheet to do that. So I'll show it to you that way. And if you go about it one of the other ways, hopefully you get an answer that's very close. But I like this equation for a first order reaction. This is first order, remember second order, and then we call it 0 or 0th order reaction. We're going to use that first order one, and we're going to rearrange it to find for k. Okay, so we're solving here for the natural log of x. Oops, let's try that again. Natural log of x at some time t. In this case, they want us to figure it out, the specific rate constant for the equation. You're using that equation. We could really do it for any of the data from our data table. We could pick any 2 of the points in there. I should say not any 2 of the points, but the original or the initial value at time 0, and then any of the lowered points in that graph or that data table would be fine. I'm going to use the one for 100 minutes. So for my equation from the formula sheet, sorry, I'm sliding all over the place here. I'm going to make my time 100 minutes, and you could use any of the data from the data table for any of the other times as well, and you'd be fine getting the same k value. So I'm going to treat t as 100 minutes and use the data that comes from that row of the data table to solve this question. So I'm just going to rearrange it for now. The natural log of x at time t, so at 100 minutes, minus the natural log of x concentration at 0 minutes, divided by negative t gives me k. Okay, and so negative t will be negative 100 in this case. And again, I'm just taking that equation from the formula sheet and rearranging it to find k or get k by itself. So if I go to my data table and plug things in, the natural log of x at 100 minutes is given in the data table. They actually have the raw data there for us, so that's kind of handy. Negative 7.013 minus the natural log of x at time equals 0, so that's negative 5.062. And then on the bottom, negative 100, and that's negative 100 minutes, if you want to think about units there. Natural logs don't have units, but the time obviously does. And when I punch that in my calculator to find k then, k will have a unit of minutes to the negative 1, and a value of 0.0195. And again, minutes to the negative 1, since I have minutes in the denominator, that's my k. All right, there's my k value. So I found the rate constant from that data in the data table. F asks me to figure out, zoom back up here to that question, find the concentration of X in the flask after 150 minutes have elapsed. Okay, so in my data table, it goes as far as 100 minutes. And they want us to figure out here, imagining that if we took this data table and stretched it out, at time of 150 minutes, what would this concentration be? What would the concentration of X be at 150 minutes? So it needs to be, at least be something less than 0.0009, or 9 times 10 to the negative 4. It should be something less than that, because the concentration will continue to decrease and approach 0 eventually as the X is used up and the equilibrium is reached. So I should say or the equilibrium is reached. So if we go down here to question F, that's what they want us to figure out. The concentration at time equals 150 minutes. So I'm going to take that same equation again and I'm going to rearrange it. So let's just kind of real quickly here, natural log of X at time t minus natural log of X, pardon me, natural log of X at time 0 equals negative kt. So that's just the equation off my formula sheet. If I set t at 150 minutes, and fill in the rest, then I can kind of take it from there. So what we're asked to find, what we're really looking to find is what will the concentration be at 150 minutes. So we're looking to find this guy right here, right? Concentration of X at time t, where t is 150 minutes. So I'm going to rearrange it to get this term by itself. And so my equation will be that the natural log of X at 150 minutes will be equal to negative k, which is 0.0195. We just found that in the last step. It's the negative 1. T, 150 minutes, and then to get this value by itself on the left side of the equation, I would need to add the natural log of X concentration at time 0. And again, we already used that in the last part, so out of my data table, that would be the adding in negative 5.062 from my data table up above. Okay. So I've just rearranged it and filled in now kind of what we all know. Again, all these values, 0.0195 is our k value. We just found that. 150 minutes was the length of time in the question itself. And then the natural log of X concentration at 0 minutes was negative 5.062 from the data table. So if I do that, if I solve it, natural log of X, punching all that into my calculator, natural log of X at 150 is negative 7.987. And no units on that because natural log doesn't have units. But that's not my answer. That's the natural log of X at 150. And remember up here I highlighted, I actually just want this part. Okay. So I need to undo natural log. And remember, undoing natural log just means taking the value that's given and making that your power on e. So in your scientific or graphing calculator, you just take lowercase e there to the negative 7.987, and you'll have your answer. It comes out to be 3.40 times 10 to the negative 4 moles per liter. And I know it's moles per liter because I'm finding up here, I'm finding a concentration of X at that time. Okay, so that would be the answer that we're looking for. 3.40 times 10 to the negative 4 moles per liter. And again, does that make sense? Realistic? Based on our data table from before? Yes. Remember we said that the concentration will continue to drop. And so as time goes by, it'll be something less than it was at 100 minutes, which was 9 times 10 to the negative 4. So now we found it to be 3.4 times 10 to the negative 4 after another 50 minutes have passed. So that makes sense. The concentration would be even smaller than it had been at 100 minutes. So a few calculations there on question 10. Some stoic stuff, I like that, to start out with, and then C through F are all kinetics-based calculations, so some good old-fashioned stoic geometry things. The other thing to kind of notice on this, and I'll point it out, and hopefully as we move into review mode with problems, you'll notice more and more, that a lot of opportunities you have to go through and cherry-pick questions or points. In other words, in this question, you wouldn't even have to do A and B at all, right? To get C through F, you could skip A and B. So what that means, not that you should skip questions, but if you're stalled or you don't know how to approach a question, don't think that means you have to quit on the whole free response question. You just skip that part and move on. Nothing from A or B becomes part of the work in C through F. Now, granted, if you can't do A, you're probably going to struggle to do B, but those two are very separated here, almost as a separate part of this question from the things below that are all about kinetics. So this free response question really comes in two halves. And it's important to know that most large FRQs, the 10-pointers in a typical exam format, the 10-point questions will often be built in that way that you can go through and sort of either skip over or jump into the question late and still be able to bank up some points on the things that you do know how to do. So if you forgot your stoic and your kinetics are good, you can do that. If you can do the first 2 parts and get some stoic points banked up and your kinetics are kind of falling flat, then you can at least do the first 2 parts out of the 6. And that feels kind of rotten, but you know, 2 parts out of 6 is far better than doing nothing. So be keeping that in mind. And that's the last of the questions I'll put in this video. If you have questions on 5, 8, or 10, or any of the other free response questions you've been assigned, let me know, and I'll try to help you out from there. Thanks a lot, and we'll talk to you later.